Hello, welcome to our 20th lesson on increasing and decreasing functions. So we've been talking about for a while clever ways to find derivatives using these techniques, but now we're actually applying derivatives using derivatives to analyze the original function. So what we're going to do today is use the derivative to determine when our function is increasing or decreasing. First, let's get specific about what these things mean, increasing and decreasing. We say a function is increasing if the graph goes up from left to right. And I'll draw an illustration in a minute. Let's actually just make this a whole sentence. And it's decreasing if it's the opposite, if it goes down from left to right. So in other words, as x is increasing, that means we're going from left to right, our graph either increases or decreases based on how the height is changing. So here's a little illustration of increasing. So as we move along the x direction in the positive, our graph is going up. And there we go, decreasing. Maybe I'll make a line, something like that, going down. Pardon that little squiggle. There, that looks better. Now, of course, these functions, they might have a mix of both. So we actually talk about increasing and decreasing on an interval, and in particular, an open interval. It's just easier to stick with that. So let's say if f, our function, is defined and we'll stick with open intervals. And let's say that these two numbers, x1 and x2, are any numbers in the interval. There we go. Now I'm also going to say that x2 is the bigger number than x1. So we are increasing if f of x1 is less than f of x2. So these are y values. Whenever x1 is less than x2. All right, so I picked two numbers in my interval, x1 and x2, where x2 is the bigger number. And if the y values follow the same pattern, if f of x2 is the bigger number than f of x1, then that means that if we have a greater y value, that means we've been going up. So that's increasing. And decreasing is the opposite. But it's still the case that x1 itself is less than x2, but now the y values have reversed. So now I have the higher y value when I'm to the left, the lesser x. Let me illustrate this. So suppose this is x1 and x2. I'm saying I have the higher y value on the left versus the right. So that's decreasing. And these are in that interval I was talking about. Okay, we can draw an x1, x2 over here as well if we like. Or, yeah, those are supposed to be points on the graph. There we go. And they're on some interval. So again, I'm increasing because as I look at the higher x value, x2, I'm at a greater height compared to when I'm at x1. And just for good measure, let's throw in constant as well. It's another alternative to increasing versus decreasing. F is constant on the interval if the y values are equal. Means there's no change. And this will be for all x1 and x2, which are in the interval. In that case, it doesn't matter which one of those two numbers is bigger because the y values will be the same. So let's look at a more specific graph. We want to find the, and I'm going to put in parentheses, open intervals, because for ease, we're just always going to assume these are open. It gets kind of weird if you try to throw in endpoints, and people don't always agree with how that works out. So we're just going to do open intervals, always. Find the open intervals where the function graphed, and I'll draw a graph in a second. We want to find the intervals where it is increasing, decreasing, or constant. So let me provide a graph. Okay, I don't like that line. It's a little better. Let's say this is 1 and this is 3. Let's draw a -1 as well. So let's say on the left side, we're going up. We reach this point and halt. Then straight line across. Let's make that look a little straighter. Good enough. And then we will go down. And then we'll turn around here at 3. So the intervals where we're increasing. So I'm talking about an interval of x values. What are the x values where our graph is going up as we read from left to right? Well, for starters, that would be this section here. I'm going up. So all the way from minus infinity to -1, we're increasing until we hit this point. And the other place where we're going up, there's 1 right here. We're going up again. So I'll just separate these with a comma. 3 and onward, we're going up. Decreasing, well, looks to me like we're going down here on this little interval. So when x is between 1 and 3, that's when we have that drop. And then constant, I see a place right here where there's no change in the y values. It's flat from -1 to 1. Okay, now I mentioned that the derivative was connected to this, and now we're going to see how that works. And that will be a useful technique for when we do not have a nice graph like this plainly handed to us. So derivatives will allow us to figure out increasing and decreasing or constant based on not having a graph. Right. So suppose a function f is differentiable at each point in an open interval. Remember, differentiable is a big word that just means you can take the derivative. The derivative exists. And we need that because we're going to use the derivative. So we need the derivative to exist at every point in an open interval. So that's pretty typical for our problems. It's pretty rare that we would not have that. So then it turns out if the derivative is positive, so f of x is greater than, f prime of x is greater than 0 for each x in the interval, then we say f is increasing on that interval. So if the derivative is positive, you're increasing. Okay, then if f prime of x is negative, I'm going to write fewer words this time, but if it's negative at every x on the interval, it's decreasing. And if 0 for every point in your interval, then you know that you're constant, right? It's like a horizontal tangent line. It's flat. So we can determine a lot about the function, whether it's increasing, decreasing, or just constant, depending on the derivative, whether it's positive, negative, or 0, respectively. So very useful tool. I want to provide a brief demonstration to show why this works. So here's a little curve. So imagine this is a piece of our function on an interval, let's say. And if we look at this point here, and we draw the tangent line at that point, well, remember the slope of the tangent line is the derivative at that point. It's the same thing. And that's a positive slope. So the derivative is positive, greater than 0. This will always be the case when your function is increasing. So this is an increasing case, and it's a positive slope of the tangent line. And now over here, if we look at a decreasing example, and I pick a point and draw the tangent line at that point, notice that this line has a negative slope. So the derivative is negative there. So this is decreasing and negative slope of the tangent line, that is. So that's the connection. Let's look at a brief example. F of x equals 1/2 x squared minus 2x. Then f prime of x equals x minus 2. Okay, well, when is x minus 2 greater than 0? Well, that's when x is greater than 2, if you add 2 to both sides of that inequality. Likewise, if x minus 2 is negative, less than 0, and you add 2 to both sides, that means x is less than 2. So these tell us when I'm increasing and decreasing respectively. The derivative is positive here when x is greater than 2. So our original function f is increasing on the interval from 2 to infinity, that's greater than 2. And decreasing, on negative infinity to 2. It's everything less than 2. So we can determine this without even needing to look at a graph. Now let's talk critical numbers really quick, because sometimes we deal with situations that are much more difficult than what we just saw. Critical numbers will help us sort this out. Critical numbers are numbers, go figure. They're numbers, we'll call them C. They are in the domain of f, our function. So that means that they're x values, and in particular, x values that belong to the function, they can be plugged in. And They are when you can have the following things happen. If the derivative at that x value is 0, that's a big one. So that's a big thing to look for. That's a critical number. If the derivative does not exist or is undefined, then that counts as a critical number. And this next one is not going to be a big focus today, but it's important to say it. Or if C is an endpoint in the domain. Excuse me, is an endpoint. That'll be a bigger focus for later. So if your domain is suddenly cut off at an x value, then you want to consider that as a critical number. So that's critical number, certain x values where the derivative behaves in these ways, or it's an endpoint. And then a critical point. So if C is a critical number, then a critical point is very similar. It's just the full point, not the x value only. So C as the x value, and then f of C as the y value. Okay. Let's do an example. Where we consider the function, this will be a polynomial. F of x equals 3x to the fourth minus 4x cubed minus 36x squared plus 5. For part A, we're just going to find the critical numbers, and then I'll show us what we use them for. Okay, we'll notice that this function is a polynomial, which means the domain is all real numbers. Any x you plug in will be just fine. So we don't have to worry about that endpoint thing. But we do need to examine the behavior of the derivative. So let's take the derivative. This is just a bunch of power rule. Bring the 4 down. So 3 times 4 is 12 x cubed. And now this part, if I take that derivative, is a negative 12x squared. Then for the negative 36x squared part, multiply the 36 by 2, you get 72, and then x. The plus 5 does nothing. Its derivative is 0. So to find critical numbers, I want to determine when is the derivative 0 or undefined. Now, this will always be defined. It's a polynomial. So we need to set it equal to 0. And so to solve, we will want to factor, right? Whenever you have a polynomial equal to 0, you typically solve by factoring. So we look for things that we can factor out in every term. Perhaps the first thing to notice is that there is at least one x in every term. So that can be factored out. It's also the case that every term is a multiple of 12, including 72. So I will bring out a 12x, which leaves us with an x squared minus x minus 6. And this quadratic part, can be factored as well. Will be a minus 3 and a x plus 2. So I set this equal to 0. It helps that we factored it, because now solving this just means, okay, x can be 0, 3, or negative 2. And that's it. So the critical numbers are those x values where the derivative is 0. Now, I haven't really mentioned the point yet. And what's the point of finding these critical numbers? They make it much easier for you to determine where the function is increasing or decreasing. Let's just focus on increasing for this problem. Part B. We want to find the open intervals where f of x is increasing. Remember that increasing means, in one sense, that the derivative is positive. So in other words, where is the derivative positive? The trick, now that we know the critical numbers, is to partition the number line, meaning divide it up. And I'm talking about an x-axis in particular. So a number line of x values, partition them by critical numbers. These will define your special regions or sections on the number line. So we'll do that we'll do that in a second. But now that we have our partition, we're going to plug in little test values to determine how does the derivative behave on this whole interval. Once you section them off this way, then every interval will behave in the same way. The derivative will either be all positive on it or all negative on it. So these critical numbers allow you to divide things up in that way. So I want to write a little more before I start drawing my number line. We plug in values from each section into the derivative, not the original function, but into the derivative, to see if it's positive or negative, or even 0. Possibly. So that was a bit of writing. Let's actually do this. So I'm going to divide up the number line into special little regions or sections, and each section will behave in the same way with regard to the derivative. This is like a little x-axis. My critical numbers were 0 and -2 and 3. So I'm going to highlight those places to show where my graph is sectioned off. So this gives us 4 regions. We have the left side over here, where the derivative behaves a certain way, and these 2 middle sections, and then the right. So we're going to plug in test points in each little section to determine the derivative's behavior. So it might help to draw some extra tick marks here for places to test. Let's start with the left side. A good point to plug in is -3. It will not be helpful to plug in -2 because we know the derivative is 0 there. I want to know what happens over here. All I need is to plug in -3, and that'll show how the derivative behaves elsewhere in this whole section. So what's more important than finding the particular value is this positive or negative? That's the main thing we're concerned about. So since I have factored the derivative right here, that makes it a little easier to determine positive versus negative. Why don't we remind ourselves, that's pretty high up, let's remind ourselves what the derivative is so we can see it. Okay, so f prime of 3. 12 times -3. I'm going to do these in my head. -6, yep, times -1. Well, the main thing to notice is that I have 3 negatives being multiplied, which results in a negative. Don't worry about finding this particular number, just know that it's a negative. So I'll go ahead and draw a minus here, showing how the derivative behaves. Next, -1 makes for a very good test point. -12 times -1 times -4 times 1. I've got a double negative here, multiplies to a positive. So the derivative is positive on that entire little interval from -2 to 0. For this interval, let's plug in 1. Or 1 minus 3. That is -2. Blank in there for a second. 1 plus 2 is 3. Just have a single negative here, which makes the whole thing negative. If you have an odd number of negatives. And lastly, for the right hand region, let's plug in 4. That's a little out there. And we'll see that these are all going to be positive. Greater than 0. So now we've plugged in our test points into the derivative, and we know this is how the derivative behaves on each region. The critical numbers split these regions up. That's why we solved for them. So now that we know how the derivative behaves in each of these sections, that tells us when my original function f is increasing or decreasing. Since the derivative is negative on this interval, that means I'm decreasing, f is decreasing on that interval. But that wasn't what the problem asked, was it? I said increasing. Usually you're finding both, but I just asked increasing, so the derivative is positive from -2 to 0 and 3 and above. So we can figure that out purely based on the behavior of the derivative. I don't need to graph it. And a quick little word of caution is that this sort of thing will be pretty common, where the sign is alternating from one section to the next. So positive to negative or negative to positive. But you do need to always test because it's not a guarantee that it'll work this way. You could have two pluses right next to each other. So you just need to be careful, always test, because it's not always an alternating pattern like this. All right, let's do something that's not a polynomial. I want to find the open intervals where my function x times e to the x. We'll do both this time. It's increasing and decreasing. So first we need to find the derivative. And we certainly won't have any endpoints with this. Both of these individually, their domain is all real numbers. So there's no endpoints to deal with. Our domain's never cut off suddenly. So we just have to worry about taking the derivative for finding our critical numbers. And I'm going to do it this way. This is a product. So I'm going to do product rule. Here I've taken the derivative of e to the x, which is itself. Here's the derivative of x. And notice I have an e to the x in both terms, so I can factor it out. Factoring helps. And here, an important thing to note is that, remember the range of e to the x? It's always positive. No matter what you plug in for x, you're going to get a positive output. So maybe I'll write that off to the side. That really helps us solve this problem. Well, first of all, e to the x, that'll always be defined. So I don't have to worry about that part. It's just when is the derivative 0? It's not going to have anything to do with e to the x. It's just going to be this part, because e to the x will always be a positive number. So I set that equal to 0, and -1 is the only solution. So my critical number C is -1. That's it. So we build our little number line. Here's 0. Here's -1. So draw my little partition there. Right, these are x values, and we will check the derivative in each region. So f prime of -2. F prime was e to the x times x plus 1. And this will be positive again. It's always positive, but this is negative. So a positive times a negative means that we are negative. Looks like 0 is a good test point for this portion. E to the 0 is 1 times positive. That'll be positive. So this means my function is increasing from -1 and above. And we are decreasing when the derivative is negative, from -infinity to -1. I'd like to take the time to look at one more. A rational function, x plus 6 over x plus 2. Let's try to find some critical numbers. Okay. An important thing to note is the domain of this thing. It's not quite all real numbers, is it? There's one thing I can plug in here, which will make the denominator 0, and that would be very bad. That would be -2. So that is part of the domain, or excuse me, the domain, well, this is the domain of the function, every real number except for -2. Now this gets a little technical, but remember I said that, where did I say it? Critical numbers are in the domain. Yep, in the domain of f, right here. So this actually means that -2 cannot be a critical number because it's not even in the original domain. So that can be a little bit of a tricky point. And by the way, there are still no endpoints on this thing because this is just like, this gives us a hole in the graph. An endpoint would really be when you have like a closed interval. So again, that's not really our focus for today. But where is the derivative 0 or undefined? Right, so let's take the derivative. That's low d high minus high d low over low squared. Notice that the x's will cancel out. These times 1s are not doing anything. And I'll have a 2 and a minus 6. So -4 over x plus 2 squared. So we want to think about, where is the derivative 0 or undefined? Notice that this will never be 0 because that depends on the numerator when you have a rational function like this. So a rational function will only be 0 when the numerator is 0. Well, that'll never be 0. It's just -4. So this will never be 0 because of the numerator. It's only 0 when the numerator is 0. So we'll never get that kind of critical number. Now, what about undefined? Well, this expression is certainly undefined when x is -2. But I cannot call that a critical number. The reason being, -2 is not a point in my original domain. It's undefined in this one too. So that gets a little tricky. So let's say also never undefined for points in domain. Of course, it's undefined at -2, but that's not in the domain.